So, welcome everyone to today's lecture. The topic will be simulation-based inference and some related methods, which are normalizing flows and denoising score matching, which is both are very important and very closely related to diffusion models. And then as part of this lecture series, the next lecture will be about diffusion models. So what we do today is that we first talk about what is simulation-based inference. So that's when we do statistical inference with the help of machine learning or deep learning. And then we will take a look at normalizing flows and continuous normalizing flows. Normalizing flows are a type of architecture that is used very often for simulation-based inference because it allows to train conditional density estimators, which you need for different methods in simulation-based inference, like so-called neural posterior estimation. And then we will see that we can generalize normalizing flows to a broader class of models, a more general class, which are continuous normalizing flows that are closely related to so-called neural ODEs, or neural ordinary differential equations. And after we're done with that, we will talk about denoising score matching, which is basically the fundament of diffusion models. And denoising score matching helps us train models that learn something, a statistical, depending on a given distribution, the models learn a so-called score of the distribution, and this score can be used via different techniques such as annealed Langevin dynamics, so that we can use the trained score model to sample from the distribution that we want to learn and kind of turn the model into a generative model via annealed Langevin dynamics. So those four topics are what we will talk about today. And then also part of this chapter, but not part of this lecture, are diffusion models and how to include physics constraints into diffusion models, which will be the topic of the next lecture. So first, let's talk about simulation-based inference. So when we have a simulator, our simulator is typically described by some algorithm. So we have some program that, given an input, produces an output. So the simulator is kind of like a model described by a computer program. That's our definition of a simulator. And what's important is that here we consider simulators that are non-deterministic. That means that when we call the simulator multiple times on the same input, it can produce different outputs. So it's a statistical model. And the reason why it produces different outputs there can be many reasons, but one very common modeling choice is that when we have observations, for example, there is some measurement noise, for example, and we include this process of the measurement noise into the simulator. But there are also other types of dynamics that are inherently stochastic, and these can also be modeled by our simulator. So we define the input to the simulator as a vector of parameters x, and then because we have this non-deterministic simulator, we say that when we run the simulator, we actually sample from some output distribution. So we write this as y sampled from this distribution p y given x. Okay, now let's kind of dive right in. Let's consider one common problem for statistical inference. And in this problem, we have a somewhat simplified real-world scenario. And our scenario is, so for statistical inference, the scenario is we have some output and we want to know, or some observation, we want to know what are all the inputs that explain the output via our simulator. So as an example, I will show you the full slide. We have this model for population dynamics. And what does this mean? So we have this population dynamics where we have a prey and a predator population that you can see on the right. They evolve over time. First, we have a higher prey population, then the predator population, which is initially very low, increases because it hunts the prey. Then the prey population shrinks. As a result, the predator population cannot sustain itself and also decreases over time. And we can kind of like this dynamic between the two populations, we can model it mathematically via a coupled ordinary differential equations, where we have two sets of populations. So like the prey are the X and the Y population, and Y is the predator population. And then we kind of have this very simple rule that describes the dynamics. And here we have a dependence on some coefficients that basically describe characteristics of the prey and predator population. And we have a total of 4 of these coefficients. And so we have like the parameters. We kind of consider those as our parameters. And now what happens, basically the simulator, like running the simulator, means solving these two ODEs, or this coupled ODE. And so how we solve it, like the solution depends on these parameters. And we are interested in finding out about what are these parameters given real-world observation data. So we have like 10 observations that we take, like this would be modeled as a continuous dynamics, the prey and predators, but say we kind of take measurements, like 10 measurements over time, and then based on these measurements, we want to know what are the parameters that kind of explain the real world. And also, so the measurements that we take, there is some measurement noise. So we can't really know the exact value of the populations, but we can just estimate it. And that's why we kind of modeled this as like taking some this log normal sampling here. This is why we include it in the simulator to kind of like model the real world measurement process. And so we have like as input to our simulators, we have these parameters. We can run the simulator by solving the ODE, adding the noise, and then kind of like taking these 10 time points. And then we kind of want to find the parameters such that it kind of like matches our observation and tell us something about what are the likely parameters X that explain our measurements, our observations. So how do we do this? First, let's kind of summarize the two types of problems that we're dealing with here. So we have the forward problem that concerns the simulator, how to kind of like define the simulator, how to obtain these samples from the output distribution, which means we kind of maybe need to find kind of like the model that explains or defines these dynamics, and we need to solve the ODE. So this is all part of the forward problem. So this is where we're using classical numerical methods. Then we are interested in the inverse problem here. So this is observe the Y, and we want to know which parameters cause it or explain it. And this is this setting now for statistical inference. And then one approach to do this is Bayesian inference. So here we really are interested in a distribution of what are all the likely parameters X. And to mathematically kind of like tackle or address this problem, we first need to define a so-called prior distribution over the parameters. So what's this prior distribution? This is basically just our first belief about the parameters x. So you can think of it as what would be our belief distribution of like what the x could be if we had no measurements or no observations. It just kind of gives us the physically plausible coefficients or the physically plausible parameters. So then after we've defined the prior, we also define the likelihood function. This is just the likelihood of observing y when conditioned on the parameters x. So like this is basically when we run our simulator with input x, how likely is it that we observe y? And kind of what we are interested in is the so-called posterior. And the posterior is the probability of the parameters x given y. And you can write this with Bayes' rule. You can write it like this. So the probability of jointly observing like of both x and y divided by the likelihood of y, which can also be like we can also expand this so that everything that we need are just the likelihoods. But we need to kind of solve this integral here at the bottom, and this is where it gets tricky, or this is typically untractable. And we call this the evidence, this integral. And not only is like the evidence very hard to compute, also the likelihood can in many cases be very difficult to compute. So if like the stochasticity of our simulator kind of only relates to the measurement process, then it's very often easier because like we have just at the end like maybe a Gaussian noise on our observation or something, then it's easier to calculate the likelihood. But in many cases when there's a more complicated control flow inside the simulator, or there's like inherent stochasticity and the dynamics that the simulator models, then this can be very difficult to kind of really compute the likelihood, especially if there are like some latent variables z that are sort of like part of the simulator and there's some randomness there, or we cannot observe them, and that means just like it gets very tough to compute this likelihood here. So as a summary, calculating the evidence can be expensive or even intractable, and then for like statistical inference there are very common methods that address this, like Markov chain, Monte Carlo methods, or variational inference for computing the evidence. The likelihood can also be intractable, and when the likelihood is intractable, it gets even much harder with classical methods. So we need to apply techniques like approximate Bayesian computation. So you can kind of rely on some summary statistics, compare some summary statistics. So like both these methods are computationally expensive and require some sort of like deeper knowledge about the problem you're trying to solve. And in this lecture, we will try to solve these kinds of problems with the help of machine learning. And so what's the definition of simulation-based inference? Simulation-based inference is just when we include machine learning in the statistical inference pipeline. And this can happen at different steps, at different levels. And there are like 3 common approaches to simulation-based inference that kind of like train a model on different parts of this equation that of this posterior equation. There's one, the so-called neural posterior estimation, that directly tries to learn a model to kind of like directly model the posterior distribution for a given observation y. But then there's also other approaches like the neural likelihood estimation that tries to learn this likelihood, and then, so this is in cases where the likelihood is not easy to compute. And then there's also the neural ratio estimation that learns this ratio between the likelihood and the evidence. And all these methods can be used in different ways inside the statistical inference pipeline to kind of like extend the existing methods. But in this lecture, we will focus on the null posterior estimation, where we try to learn a model for the posterior directly. And kind of a different or like more detailed way of kind of like defining null posterior estimation would be that we train a so-called conditional density estimator, which we call this Q theta x given y. So like it gives us the density, the likelihood of x given some observation y. And so in this conditional density estimator that we try to learn, the weights theta are here the model weights, and this should be close to the real posterior x given y. Now kind of the challenge here is that what is the training data, basically, because we don't know what is the posterior for many of these problems. That's why we want to train a model for it. And so kind of how do we solve this problem without generating, like knowing the actual posterior? And kind of the really cool thing about neural posterior estimation is that there's a method to train this conditional density estimator, Q theta, without knowing what is the true posterior, but only being able to sample from the prior and then run the simulation. So basically everything that we need to train our conditional density estimator is being able to kind of run the simulator, get many simulations for some input parameters. That's all that's needed. So what is an unconditional or a conditional density estimator? So basically we say for conditional density estimators, or first unconditional density estimators, we consider some like parameterized model families. These here, like these Q theta with x as the input. And all of them are parameterized with weight theta. And for every weight theta, this kind of model family needs to be a density. So this is very important. So for it to be a density, that means that like the output of our model is always non-negative. And it satisfies that if we integrate over all, like the input space of all the parameters, integrates to 1. And so this is very important, that kind of this property is always satisfied, and it's actually not like super clear how kind of to define these model families. But we will see in the next slides that normalizing flows are well suited for this. And we can use normalizing flows to kind of build density estimators. And kind of when we train this model family that kind of like represents these densities, we want that this normalizing flow, or like this conditional density estimator, is close to the target density that we try to learn. And basically there's not much difference between training unconditional or conditional density estimator. We will kind of like look at the details a bit more closely in the next slides. Okay, so as a summary of this chapter, if we look at classical methods for statistical inference, they very often have already a lot of research that has been done and come with a rich mathematical theory. They are like very flexible, so it's easy to replace parts of the, like to change the simulation, to change likelihood functions, to change the prior, but they can be computationally expensive. They suffer from the curse of dimensionality, and sometimes it's difficult to represent arbitrary priors. For example, if we think of priors being like real, like, you know, when you don't have like mathematical models often, but you kind of like have really high dimensional data like proteins or like some medical data, then there you have a prior there as well. And this prior is sometimes difficult to express mathematically, but this is where we can really use the power of deep learning. And then on the other side, we have these learning-based methods like posterior estimation, neural likelihood estimation, or neural ratio estimation. And like they can be very fast once they're trained, and they're not as affected by the curse of dimensionality as the classical methods. And it's easier to represent like new or stronger, more complicated priors via these methods. But at the same time, they often like more rigorous theoretical guarantees because we need to train a model. There is this upfront training cost. Once you've trained your model, it's generally not as easy to change some like parts anymore because we have trained a model assuming certain certain relationships or certain things. Okay, now before we take a closer look at how normalizing flows work, we will talk about what is actually the training function for training these conditional density estimators. And the fundament for kind of defining what is the training function is the Kullback-Leibler divergence. So if we remember from the Intro to Machine Learning class, the KL divergence can be defined between two probability distributions, P and Q, that have two densities, P and Q, and it's defined like this. So we integrate over the parameter space or the domain. Here we have the density of P, and here we have the log of the ratio of the densities P and Q. And now what are some properties of the KL divergence? It's always positive, and it's zero only if P equals Q. So what we want to do is we want to, so P is kind of like the target density that we try to learn, and we want to learn it via a model, our conditional density estimator Q theta, and we want to optimize theta such that kind of like it minimizes the KL divergence between P and Q. So let's simplify the KL divergence. We can write the KL divergence using the definition like this. Then we can write this also as an expectation. Now we have the expectation of the log of this ratio. We can also reformulate that. So we can write the log of a ratio as the log of like px minus log q theta x, and then kind of reformulate. We can write, like we can expand the expectation. So we have two expectations now, so we can do this. Okay, now what we see is that the first part of this expression doesn't really depend on theta anymore. So it's constant with respect to theta. And that means that when we want to optimize the KL divergence, we kind of like don't care about this part because it's constant with respect to theta. And the only thing that changes is here this right expectation. So this is actually what we want to focus on. So we want to minimize the KL divergence between those two. That means that's the same as minimizing this expression here. Okay, and it's very easy to kind of do the same mathematics for the conditional density estimator, not just the unconditional one, but also the conditional one where we condition on some input, additional input, or some observation y. So we can first write our loss as this, where we sample y just from all the observations, and we sample here from the posterior. So this is what we would like to optimize, and we can rewrite this using Bayes' rule. And these steps, we can rewrite this as this term here at the bottom. And this term here kind of like changes how we do the sampling. So instead of sampling some observation y from the distribution of observations, then having some samples x from the posterior, it's sufficient, so it's the same as sampling from the prior and sampling the observation from the simulator, and minimizing this term inside the expectation here. So, and the last thing is something we can actually do. So using kind of like just some easy transformation from Bayes' theorem, we can transform this expectation into this expectation, and in this expectation we just need to sample from the prior, run the simulator. So this is really something that we can do with our training data when we have some training data set. Okay. So next, let's talk about normalizing flows. Normalizing flows are in general transformations of a simple Bayes distribution, which we call PZ, into a complicated target distribution, PY. And this transformation doesn't happen in like one step, but there is a sequence of transformations, and the sequence is made of these transformations, which are themselves invertible indifferentiable mappings. So we really need this because we want our normalizing flow to be bijective, and we want it to be differentiable. And this here is a visual summary. So we have the Bayes distribution, which is typically a simple Gaussian distribution. Then we have one direction, so because this mapping is invertible, this normalizing flow, we have the generative direction, which takes a point from the Bayes distribution and transforms it into a point from the target distribution. And you have the other direction, the normalizing direction, where you take a point from the target distribution and can map it to a point on the Bayes distribution. So how can we use this? So first, let's kind of like write down the all the ingredients that we need. So we have, when we have a single invertible mapping G, and then we write F as the inverse of G, then you can write the generative direction and the normalizing direction like this. And what's like really important for normalizing flows is that the likelihood, because we have these differentiable invertible mappings, we can also compute how the likelihood changes during the generative and normalizing direction. And actually you can compute the likelihood like this. So basically when you have a point on a target distribution, you want to know what is the likelihood, you can look, okay, when I map this point to the Bayes distribution, this is what happens here in the Fy, when you have the normalizing direction, you kind of map this point from target distribution to the Bayes distribution. So you ask what is the likelihood of that point mapped to the Bayes distribution. The Bayes distribution is a Gaussian, so we can actually compute the likelihood there. And then you need to account for this second factor, which is this determinant of the Jacobian here. And this can also compute via automatic differentiation. So this is like tractable to compute, and we can basically chain these simple invertible mappings together to kind of like we compose them and then we can kind of write our full normalizing flow as the composition of these simple transformations. So we can define a normalizing direction, a generative direction, and basically we still need to kind of like track how the likelihood changes, but we can very easily show that when we know how we do it for the simple single mapping, then basically we can do the same math for the composition of these mappings. And so the probability density of a point in a target distribution can be computed like this. So one kind of like important technical aspect is that usually when we implement things, we don't kind of like directly model the likelihoods, but the log of the likelihoods, because this is numerically more stable. And so we kind of know how to build these normalizing flows when we know like the differentiable invertible mappings, but kind of just like coming up or finding these mappings is also a problem of its own. So there are different types of normalizing flows where these mappings are different, and there are, for example, like one popular class of these mappings are coupling layers or autoregressive flows, and we won't talk about them in detail, but if you're interested, check out these two papers here that give a very nice introduction into how you can build these layers and these normalizing flows. Yeah, so to summarize, it's like, because also for normalizing flows, you also want to kind of use them as a generative model, and you can kind of like use them as a generative model by drawing a sample from the base distribution, the Gaussian base distribution, and then you get the sample by just going inside the generative direction of your normalizing flow. And when you want to compute the likelihood of a sample in your target distribution, you map it to the base distribution and you compute this log of the determinant, like you keep track of this along all the composition of all these mappings, and then you can use that to get the likelihood of a point in a target distribution. So the reason why we don't take a deeper dive into normalizing flows is because we actually take a look now at continuous normalizing flows, and for that we first take a look at so-called null ordinary differential equations. And so these are very strongly motivated by the success of residual networks, or ResNet. So if you think of a ResNet, you can write like the skip connection inside the ResNets like this here, where you have like that the updated state is sort of like the previous state plus some neural network, some layer that kind of does some transformation to this intermediate state and adds this to like the previous input. And so like we have these update steps via the skip connections for ResNets. And kind of the idea is now that these look kind of similar to how you would solve an ODE with the Euler steps. And basically what they're saying is that, okay, these skip connections are basically like Euler steps with like step size 1. And each layer has its own parameter. But what happens when we say that instead of like each layer having its own kind of parameter, we have like one big global parameter for all the layers, and then we have to each layer an additional input that kind of tells the layer, you know, how deep is it, like which layer is it, like an index for the layer. So instead of having, layer weights for each layer. We have one big weight vector, and each layer gets this weight vector and gets an additional input which tells it what index it is. And now what happens when, instead of like considering this as like an Euler step with step size 1, we actually model this as a type of like continuous dynamics. So we say that instead of having these Euler steps, we have like something like an ODE, where we say the intermediate state of inside my neural network is not, the update rule is not these skip connections, but instead we kind of like say, well, we have an ODE here where with time, so we introduce a new parameter time here, but the time actually corresponds to like the index of the layer. And we say that we don't have like these distinct layers, but we have like a continuous change of the layers over time. So we have the time input as part of the layer. And we say, okay, we can write this as this ODE, where the change over time of the intermediate state is continuous. And this change is given by this f here, but the f is kind of like parameterized by theta and by t. And so this defines the so-called neural ODE. And you can see a visualization here on the right. Now the thing is, we can do the same for our normalizing flows. So instead of having these small transformations where like each layer is like these transformation, we can actually define our network in a similar way. So we have the integration over time as basically doing like a forward pass in a neural network before. Now it's basically solving this ODE, integrating it over time. And how it looks like is basically now that we have here on the right, we have our base distribution again. At the top, we have the target distribution. And instead of these discrete layers, we kind of have a continuous dynamics field now, which is learned by our model. And this field changes over time from t equals 0 until t equals 1. And so you don't have like individual transformations anymore. Everything is like a continuous dynamics transformation that resembles an ODE. So these are like just the mathematical parts of like how we replace the parts of the neural network or the part of the normalizing flow now with this continuous version. And now what is really nice is that when we have an ODE, it's by design invertible and it's also differentiable for the like parameters, like for theta, it's also differentiable. And that kind of makes it a normalizing flow, a continuous time normalizing flow. And the only kind of like really difficult part here is now that how do we kind of like keep track of how the probability changes for the generative and normalizing direction. Before it was via this determinant of the Jacobian, but now it's different. And there is one rule in analysis that kind of tells us how it should be computed. And this rule is the instantaneous change of variables formula. And it tells us that the likelihood of like a sample along like this path that resembles our transformation is given by this, where we have here the trace operation of the Jacobian. Okay, and this basically answers our question. Now, let's kind of like put everything together and write like a summary of how to train a continuous normalizing flow for simulation-based inference to learn the posterior distribution. So we have a training data set that we need to generate. So this is the expectation. This was part of how we derived the loss function. So in this expectation, we had to kind of sample from the prior, then run the simulator. So we do this a few times, as often as we basically can run a simulator, given like maybe running a simulator can be expensive maybe. So there's like a budget here, but we connect all these pairs, or we collect them, we collect these pairs inside a training data set. Then this was the training objective that we had worked out. So to compute this with a continuous normalizing flow, we need to solve an ODE to work out both how our kind of like we need to map a point from the target distribution to the base distribution via this ODE, the null ODE, and at the same time keep track of how the likelihood changes along the path. And we can do this like by writing it down like this. So this is basically the ODE we actually need to solve. And here in this ODE, we first have that we transform. So like we start here at the target distribution. So this the variable along the path that we integrate, that's the z. And basically at time 1, where we are at the target distribution, this is equal to our sample x. And this here is the change of the likelihood along the path. And basically we say that at t equals 1, this expression here is 0, because it also evaluates to 0. And then, so these are the initial conditions, and then our dynamics are given here via this. And the dynamics tell us, okay, as we integrate over time, the likelihood changes, like this trace operation for the Jacobian here, and then the dynamics, so how we transform our sample x to a sample from the base distribution, that's basically given by here our neural network parameterized by theta. And we solve this, basically we solve this going from the target distribution to the base distribution. We solve this via an ODE solver using automatic differentiation to get the solutions. So these are the solutions at time 0. So Z0 is the sample that corresponds to our sample in the target distribution, but Z0 is like the corresponding sample at the base distribution. And this here is like the lower part here is exactly the change of likelihood. And yeah, so we can evaluate the likelihood, and using our automatic differentiation, we can also calculate the gradients with respect to theta to minimize our training objective. Okay, and then we can use the gradient to update theta and do the optimization using our favorite optimizers. Okay, to summarize, or like to give like some assessment of how well this works, yeah, we can compute the gradient here for a continuous normalizing flow, but it will be expensive. At the same time, this is also a nice way to solve the problem, because it directly, like this kind of training directly maximizes the likelihood or minimizes the KL divergence. So this is like a proper maximum likelihood training, and it's generally a good, like it's a very well motivated approach to use or to share these parameters theta across different time steps. But as I mentioned, calculating the gradient is not so easy. So there are larger memory requirements and training inference costs for solving this ODE. So that makes it very difficult to scale. And we need other methods. And this is why in the next part we will talk about an alternative way to train a generative model. And this is basically, as I already mentioned, the fundament of diffusion models. So let's talk about score matching. So with like a normalizing flow, we directly learn the target distribution. This is like well motivated and makes a lot of sense, but at the same time is also something very difficult. And the problem is that kind of like when we learn our model, our conditional density estimator, it is not, like when we learn it, it's not local. That means that when we kind of like increase the probability of some sample in like, yeah, basically imagine you have like on the left, you have some samples, on the right you have some samples. If you increase the likelihood of samples on the right, you could, like you need to decrease the likelihood of the samples on the left. So there's like this global dependency that kind of makes everything difficult. And what we can try to do instead is to learn a property of this target distribution that doesn't have this global dependency. And so we kind of learn a local properties of the target distribution. And these local distributions, or these local properties, are sort of like the local kind of like property of the distribution that we learn is this score here. And the score is nothing else mathematically than the gradient with respect to x of log px. And so this is what we want to learn. It's a local thing because of the gradient. And we try to learn this with a network S theta. So below you can kind of see the difference or what the score means. So when we have a target density, the score basically tells you that, okay, I see they don't match perfectly here. I should double check this. Basically the main problem is that you have, when you learn a PDF, the density, it needs to be normalized. You have this global dependency. For the score, everything is local. And as I already said, we want to learn the score via this network S theta. And what we, like our training objective becomes minimizing the so-called Fisher divergence. So the Fisher divergence is this expectation here, and we want to minimize this. The problem is that we don't know what is the ground truth score. So the only way that P is usually accessible to us is via samples from P. And these samples don't tell us what is the score, because we don't know how to, like we don't even really know what is the likelihood of samples. We just have the samples. So there are two solutions to this. One solution is so-called implicit score matching, which we will not focus on, but what we will do, or what we will focus on, is denoising score matching. So for denoising score matching, it kind of like already is apparent from the name. It has something to do with denoising, with noise. So I will explain exactly where does the noise come from. So in denoising score matching, we consider not our original data set or our original target density, but a perturbed version of it. So for like if we have a training data set with these samples x1 to xn, we consider a perturbed data set where we add noise to each sample. And the way we add the noise to the samples is via this noise process. So we add Gaussian noise depending on some parameter sigma. We just add the noise. And here on the right you see an example. S is our data set. Then we add the noise perturbed. It looks like this. And let's for now assume we just keep this noise level fixed. But what's also clear is that if the noise level is smaller, then the perturbed distribution is closer to the real target distribution that we want to learn. So we can also write that as sigma increases to 0, the KL divergence between these two is 0. So one thing that we can do is we can write down an expression for the score of, or like first we can kind of write down what is likelihood of the perturbed data. So for that, so the likelihood of the perturbed data is just this expression here that we can write as the integral. So like basically we integrate over all samples from the target distribution, and we kind of look at what's the likelihood of the perturbed data being generated or coming from the data x that we integrate over, and this is just our likelihood of the perturbed data. And we can write it also like this. So the likelihood, the density of the perturbed data is just this expression here. So this conditional density is a Gaussian because like we know what's the process. So we add, so given x, we just add the noise times sigma. So it's basically a Gaussian with mean x, the perturbed data. And therefore we can write this conditional density in this form as a Gaussian here, where the mean is basically x. And the standard deviation depends on the sigma. And now we can very easily compute the score of this conditional density. Yeah, so because it's Gaussian, we can do some easy math for transformations, and this is the score of the conditional density. Now, how does this help us? Because here, like first of all, we learn the perturbed data set, which, okay, is fine because we have just a small perturbation. But here we just know the score of the, when we condition on like x. So how does this help us? Because we want to learn the score when we don't condition on x. And here is where a really important theorem comes in. And that's this theorem here. So it says that we can train S theta to approximate the score of the perturbed data set. And the reason why this works is that basically when we optimize our network, so this is like the first line here is what we actually want to do. So we want to learn a score for the perturbed data set, so where we don't condition on x. But it says that like when we try to find a model that kind of minimizes this, then it also minimizes the objective here on the second line. And the objective here on the second line is that we kind of like take the expectation by sampling from the target distribution, which we can do since we have samples from it, and then computing or like perturbing the sample and training S theta to match the conditional score. And kind of like these two objectives, like minimizing these two objectives, gives us the same minimal theta, or best theta. And yeah, so this is like a really groundbreaking theorem because it allows us to really train a model to match the score in a scalable way. Because all of this can be computed very efficiently. So it's just, you know, a sampling, perturbing, and then this very easy Gaussian expression. So now assuming that we have a model for the score, the question is, how can we use it to get a generative model? So how can we kind of like use the score to get a generative model where you can actually sample from the model? And this is done using Langevin dynamics. So Langevin dynamics tells you that basically if you have some some distribution that you want to sample from. So like in our case, distribution would be P of X, and you have like an initial distribution that you begin with. You consider this iteration rule where you have like particles that are initialized from this initialization distribution, and each particle you update via this rule, and in this rule you kind of like take the previous particle, you add, like you go a little bit in the direction of the score, so this kind of like moves in the direction of where the likelihood is higher, and you also add a little bit of noise every time and every step. And you repeat this many times from E equals 0 to K, and yeah, so the noise is also Gaussian here. And when kind of you do this for all the particles, you repeat this, you kind of say you let the epsilon go to 0 and the K to infinity, then actually you will get the real distribution that you want to sample from, like this P distribution. So if you just do kind of like iterate this with the particles, then in the end you will end up with samples from Px under some mathematical regularity conditions. But this is how we can use it in machine learning. And you can see this here on the right, like what happens. The blue points are the particles that are like initialized uniformly over the space, and then we have the contour lines of the distribution that we want to learn, or that we already have learned with our score model. And the arrows are basically the scores. So these point in the direction where the likelihood increases. And now we just run this. So we do the iteration, and it looks like this. Here we have used not the real score, of course, but the score that we have learned with the neural network using denoising score matching. And you see that basically the particles like move in the direction of where the likelihood is higher. Okay, so as a summary, we have our data samples. We use these data samples to train via score matching a model that learns the score. We use this score via Langevin dynamics to get new samples. So this is this already works well. You can use this, but there is one problem here, and that is that it kind of works but doesn't work very well. And the reason why it doesn't work very well is that it's kind of difficult to initialize our samples. Like the first initialization of the particles, that's actually the hard or difficult part. Because the problem is the following. So when we have, like, assume these two clusters here are our, like, they represent our target distribution, and then we have a higher likelihood around these 2 points. So close to these 2 points, we have a high likelihood. This means that basically our model is only trained ever when we are already very close to the likelihood, like to the high density regions. So this is where our model is trained. And the problem is that, especially when we're dealing with high dimensional data like images, that like the initial samples will be very, very far away from any high density regions. Now the model is never really trained on these low density regions. That means the scores that the model outputs are just not very reliable, because they are just like inside the inside these low density regions for the initial samples, but we trained the model on these high density regions. As a result, our method doesn't work very well. So what can we do to solve this problem? And the kind of solution is that we don't use a fixed noise level or perturbation strength for the data set, but kind of train our model using a different number of noise levels. Yeah, so we train, for example, we say we have now 3 noise levels, and so basically when we have a high noise level and train the model, that means that, you know, we don't have any more these low density regions, because our kind of like target distribution is now really like spread out, like we're dealing with a lot of noise, high perturbation. So our model is really also trained now on what used to be these low density regions. So training with like this high noise solves the problem of these, like the model being not trained in low density regions. But now that means that the data that we actually, like the score of the distribution that we learn, it's actually for a distribution that is very, very noisy. And that's very far away from the target distribution that we actually want to learn. And so what is our solution to this is that we just have different noise levels. So we have a model trained, or like an input to our model is like the noise level, or we have different models for each noise level. Basically, we start with a high noise level, then do the Langevin dynamics, then we kind of have already, like we already made sure our points are now in like higher likelihood regions, like regions where there is a higher likelihood for the given noise level. Then we decrease the noise level, so we go from sigma 2 to sigma, from sigma 3 to sigma 2, and then we kind of repeat the Langevin dynamics, and we do this many times. And this is the annealed Langevin dynamics. So there are multiple noise scales, and we just repeat the Langevin dynamics for each noise scale. And this solves the previous problem. So we, to kind of visualize it, we start here with high, then medium, then low noise, and so this works much better now. Okay, to summarize. So denoising score matching is built on this nice theorem where we can kind of exploit that we just know the conditional scores, but just knowing the conditional scores allows us still to learn a model for the score of the perturbed data set. And this works like this is very scalable and works even for high dimensional data. That makes it also much more scalable than continuous normalizing flows. But we have this problem that, like when we sample, for example, via Langevin dynamics, that we need these different noise scales, and we need to kind of like start with high noise scales and then kind of like decrease the noise scales over the course of the sampling. So that means we need to kind of iteratively, or like we need many evaluations of the network. And another disadvantage for now is that we cannot directly compute the likelihood anymore. So there are solutions here, of course, but for the annealed Langevin dynamics, we cannot compute the likelihoods anymore. So when we train our model, it's no longer a maximum likelihood training. So that was the end of today's session. Next session will be about diffusion models and how all this, the denoising score matching and Langevin dynamics, how it relates to diffusion models. And then, yeah, so next lecture will be in more details about diffusion models and continue today's lecture. Okay, thanks everyone. Have a good day and see you next time.